Hello, Chem 1A. This is Chapter 7, Lecture Video 8, and we're going to be talking about molecular effusion and diffusion. These might be two new vocab words for you, so let's define them. Effusion is defined as the leakage of a gas through a small aperture. Now, this is just a fancy way of saying small hole in a container. Right? So, an aperture is just a small hole. If you might have seen the word aperture if you're really into like really good cameras. You can change the size of the hole for your light detector on your like DLSR camera. But it's basically just a small hole in a container. Now, diffusion is similar to effusion, but it's not quite the same. It's actually the spread of a gas throughout an open space. Often, after a gas effuses out of a container, i.e. leaks out of a small hole, it will then diffuse to fill the larger container it just leaked into. For instance, if we look at this picture here, we have bromine gas inside that little Erlenmeyer flask. As soon as we pull this stopper out, the gas will effuse out of the Erlenmeyer flask and then diffuse to fill the entire container that it's now leaked out into. And so once we've finished effusing and finished diffusing, we have our results here where the entire container is equally filled with the Br2 gas, the bromine gas. All right. So that's kind of a good example of effusion and diffusion. Now, there's a law here that we can use to calculate molar mass or rates of effusion of a gas, and that's Graham's law. Graham's law basically states that the rate of effusion of a gas out of a container is inversely proportional to the molar mass of the gas. Now, in the last lecture video, we talked about how the heavier your molar mass, the slower your gas moves. So hopefully that makes sense, right? If we're leaking out of a container and we're really big, heavy, and slow, then we're not going to leak out very quickly. So the molar mass is very large. It's going to slowly leak out of a container because it's moving slowly. However, if we have a really lightweight gas, that gas is going to be moving very quickly and therefore will leak out of the container faster. So we have an equation for this, and that is rate of effusion 1 over rate of effusion 2 is equal to the square root of molar mass. I have molecular weight there as the symbol, but that's the same thing as molar mass 1 versus, molar mass 2. Same difference. In most cases, when we're using this type of equation, we're given rates of effusion. We're given at least 3 of the 4 variables in the equation. All right. And sorry, this is molar mass 2, and this is molar mass 1. I mislabeled that. So the 1 and the 2, we can say any of the values that we get is effusion 1 and any of the values is effusion 2, just as long as we're consistent, right? If the rate of effusion of oxygen is some number and we're saying that's rate of effusion 1, then the molar mass of oxygen has to be molar mass 1 in the equation because we got to stay consistent with our labeling. All right, so let's do an example problem. We have carbon dioxide and it effuses out of a pinhole at a rate of 0.232 milliliters per minute. Another gas that we do not know the identity of effuses out of that same pinhole at 0.363 milliliters per minute. What is the molar mass of the unknown gas, right? Well, I know what carbon dioxide is. I know this is CO2, and I can calculate its molar mass, 44.01 grams per mole, right? Now, we can use that equation that we just learned, rate, I'm just going to kind of abbreviate this, EFF for effusion, 1 over rate effusion 2 is equal to the square root of the molar mass 2 over the molar mass 1. I'm just going to call this molar mass 1. And therefore, this guy, our 0.232 milliliters per minute, is EFF1, or rate EFF1. And then our 0.363 milliliters per minute, that will be rate of EFF2. And we're going to solve for molar mass 2. So let's plug in, right? So we have 0.232 milliliters per minute over 0.363 milliliters per minute is equal to the square root of molar mass 2, what we're trying to solve for, over the molar mass of CO2, which is 44.01 grams per mole. Now, if I want to solve for this, I need to square both sides, right, so that I can get rid of that square root. So I'm going to square both sides and divide those two numbers as I go too. So let's do that, and then we'll get our number. And what we get is 0.408 is equal to molar mass 2 over 44.01 grams per mole. And so now I just need to multiply both sides by 44.01 to isolate our molar mass 2, right? And so what we get finally is molar mass 2 is going to be equal to about 17.97 grams per mole. And so there's our answer. And really this eventually, if we do sig figs, ends up being 18.0 grams per mole, because we should only have 3 from our original values. All right, so if you have any questions, as always, please let me know, and I'm always happy to help.